Dear viewers, welcome to our TCE LearnEasy series on civil engineering concepts. In this lecture, let us obtain the Euler's crippling load or buckling load for both ends hinged case of a column. So we have four end conditions of a column, that is both ends hinged, both ends fixed like this, one end fixed and other end hinged like this, and one end fixed and other end free like this. In this case, let us take the first category, that is both ends hinged. So draw the end conditions. Say this is hinged, so this is hinged. The load, axial load is applied P. Let us consider a section XX at x distance from here. Let us consider a section XX at x distance from here. P is the critical load or buckling load. Y is the deflection at the considered section or the section taken. Now we need to find the bending moment at XX. Bending moment at this section. Say let us imagine we are at this point. So we want to find bending moment at this point. So the load available is P and the distance is Y. So this load P will cause a bending moment of P into Y about this point. That is MXX. That is bending moment about XX. And we should see the nature of the bending moment. So if we are standing at this point and look at the force, so it will cause an anti-clockwise moment about this point. In case if we are here and if you see, then load will cause a clockwise moment. So it will cause an anti-clockwise moment. So anti-clockwise should be considered as negative. So bending moment at XX equal to, that is M equal to minus P into Y. Load into distance. Load is P, distance is Y. Minus sign is due to the moment being anti-clockwise. Then we have the second order differential equation of all flexural problems or all bending problems. This is the second order differential equation which will be useful for all beams or flexural problems. So we will substitute the values here. So EI d squared by dx squared equal to minus Py. Bringing this minus Py to left side, EI d squared by dx squared plus Py equal to 0. Now dividing this entire equation by EA, that is we are dividing here, we are dividing here and we are dividing here. So if we divide here, we get d squared by dx squared. If you divide here, P by EA into Y equal to 0. So this is the second order equation in Y. So we need to obtain the solution for Y. Y is the displacement or deflection at any section X. So the solution for this differential equation, second order differential equation will be, say, the complementary function plus particular integral, which you better study in mathematics. So we are going to use that. We can use that and we can get the general solution. However, the general solution can be remembered like this. Say, even if you use that particular integral and complementary function, you will result in with this. So you can check at a later stage. Now let us take this general solution for this equation as y equal to, so you will be getting a cos alpha x plus b sin beta x. So a cos alpha x. So here will be a cos x root p by a plus b sin x root p by a. This will be the general solution for this differential equation. So please check the solution with the mathematical principles which you have learned earlier. Okay. So our time being, we can take y equal to a cos x root p by ea plus b sin x root p by ea. So this is equation 1. Now these are the constants of integration a and b. We need to find the constants of integration using the end conditions or the boundary conditions of the problem. So let us take the boundary conditions. Say if we take a column of this type that is hinged at both ends, we very well know that the bending moment at the hinged supports is 0. Bending moment at hinged support is always 0. So the bending moment at A is 0. Similarly, the bending moment at B will be equal to 0 since they are hinged. So you can use these two boundary conditions. That is, at this point, the x takes the value of 0. And at this point, x will take value of L. So we can write the boundary conditions at when x equal to 0, y equal to 0. Say this deflection is 0. Here we don't have any deflection. Similarly, here we don't have any deflection. Whereas here at section x, we have deflection y. So at x equal to L, the deflection is 0. So the boundary conditions are when x equal to L, y equal to x equal to 0, y equal to 0, and when x equal to L, y equal to 0. So we need to substitute these two boundary conditions in this equation 1 to get the values of the constants of integration. So using boundary condition 1, put x equal to 0 here. So this will become, if we put x equal to 0, a cos 0 plus b sin 0, this term will get cancelled. So a cos 0 is 1. Here y equal to 0, therefore we will be getting a equal to 0. A equal to 0. Then using the boundary condition 2, that is you need to put x equal to L. So and y equal to 0. So put y equal to 0. In the place of x, put L. So a cos L root p by Ea plus b sin L root p by Ea equal to 0. And A is already 0. A is already 0. Therefore, this term will get cancelled. So, we will be getting b sin L root p by A equal to 0. So, this we get from the boundary conditions. So, among this, either b should be equal to 0 or L root p by sin L root p by Ea should be equal to 0. Only these two are possible. If this equation is need to be satisfied, either b should be equal to 0 or sin L root p by equal to 0. If you take b as 0, then you will not get solution for this deflection, because we have the equation y equal to a cos x root p by a plus b sin root p by a. A is already 0. Now if b is also 0, then you get y equal to 0, which is not correct. Therefore, b can't be 0. B can't be 0. Only sin L root p by a should be equal to 0. So sin L root p by a equal to 0. If this sin L root p by a should be equal to 0, then this here we should have either pi or 2 pi or 3 pi, etc. Because we very well know that sin n pi equal to 0 and cos n pi equal to minus 1 power n. Sin n pi equal to 0 and cos n pi equal to minus 1 power n. Therefore, this should be equal to either pi or 2 pi or 3 pi, etc. So L root p by A should be equal to pi, 2 pi, etc. Then we will get this condition or equation satisfied. So among these values, taking the lowest value or the least value, L root p by A should be equal to pi. This is the lowest significant value, pi. Therefore, if you square on both sides, you will get L squared p by A equal to pi squared, or p equal to pi squared Ea by L squared. This is applicable when both ends are hinged. So this is the Euler's formula for finding the crippling load or buckling load of a long column when both of the ends are hinged or pinned. So if you know the Young's modulus, and if you know the moment of inertia, and if you know the effective length of the column, we can find the load carrying capacity of the long column. So thank you all for listening. Please keep subscribing and share among your network. Thank you.